transform method together with Wiener-Hopf.
Great. Well, thank you for the introduction. Thank you also for the opportunity to come and speak to you. So I'm going to be talking about scattering problems, and I'm going to try and set this talk up as presenting a method that could potentially be used in this community and also used to verify solutions to Wiener-Hopf type problems. So just going to launch straight in. I'm interested in the 2D scattering problem governed by the Helmholtz equation in some domain D. And associated with this problem, some typical boundary conditions that I'm sure we're all familiar with are Neumann boundary conditions, Dirichlet boundary conditions. You can have a mixture, Robin boundary conditions if you're modeling impedance or porosity. And then another type of boundary condition that I'm going to talk about is that of elastic deformation, which is a bit more complicated, and even for a single plate problem, gives you a matrix Wiener-Hopf problem. And then, of course, I'm going to look at, because I'm looking at scattered fields, I'm going to impose the Sommerfeld radiation condition at infinity. So this talk is all about hopefully an effective numerical way to compute Q. It's a brief sketch. I'm going to discuss building a method to solve these types of problems. Then I'm going to look at the canonical problem of a rigid plate and how you can solve that efficiently. And then I'm going to look at two applications, that of elastic plates and then also perforated screens and Robin boundary conditions. And I'm going to end with some open problems, which I'll be interested to discuss with people as well. And the take-home message is that this method I'm going to present is an efficient way of solving these types of problems, and hopefully will be of interest to the types of things you guys are looking at. Okay, so I'm basing this method on the unified transform, which, for those of you familiar with it, arose in solving integrable nonlinear PDEs, and potentially can cause some confusion when it's presented in complex analysis form. So I'm going to go through it hopefully in a more familiar way. So if I assume that Q and V solve the Helmholtz equation in my domain D, then it's straightforward to convince yourself that this differential form here vanishes. And assuming for the time being that everything behaves well at infinity and all the integrals converge, we can plug this into Green's theorem, and we end up with an integral over the boundary of the domain where this guy vanishes. And if you choose a specific choice of V to be these plane waves with this kind of weird looking parametrization for different lambda, then you end up with a Fourier type integral equation, right? So I've got the what looks like a Fourier transform along the boundary of the domain of the Neumann derivative of the solution Q, and also the solution itself, Q, along the boundary. And you should kind of view this as a Fourier transform of the boundary integral equations, right? Now it's generalized because I haven't said anything about the domain yet. So to connect this with kind of existing techniques and the Wiener-Hopf technique in particular, let's look at the very simple case of collinear plates in the y equals 0 plane. And if I do that and impose a Neumann boundary condition, then I end up with this integral equation here, where this is just the standard Green's function, the Hankel function. And then if I take the Fourier transform with this weird parametrization of the frequency, I end up with exactly the same integral equation I had on the previous slide, but now I also have the restriction of these lambda values. Okay, that's all very well. And then, as I'm sure everyone knows, if you then make another substitution, you can recover the Wiener-Hopf equation as well with this this integral kernel here, Wiener-Hopf kernel. So why is this useful? Why am I presenting something that you're all familiar with in perhaps a weird, strange way? Well, first of all, like the Wiener-Hopf method, this is a nice relation because you turn convolution with singular integrals into multiplication in Fourier space. You can also generalize the Wiener-Hopf equation to arbitrary domains, as I've mentioned previously, and you can also generalize it to separable PDEs. You don't have to just look at Helmholtz or Laplace or equations like that. And for some problems, it allows you to actually solve the problem analytically where previous Wiener-Hopf approaches didn't work. And also kind of something that I want to look at in the future is whether you can use this, the method that I'm going to present in 3D, and whether this can kind of give you a Wiener-Hopf for 3D problems. Okay, so let's look specifically at turning the relation I showed you into a numerical method. So consider the case where I have a single plate as my boundary. So I have the domain boundary is just a single straight line, and I expand Q and the normal derivative in terms of basis functions. So Sj for Q, Tj for the normal derivative. And then if I introduce this what's really just a Fourier transform and evaluate the relation at a specific lambda I end up with a linear relation between the coefficients of the expansions. Okay, very simple. And if I do this at lots and lots of points, I can build up a linear system which couples the different coefficients. Okay, and this matrix is just formed from the Fourier transforms of my basis functions. And in a typical problem, I'll know some linear combination of this, so I can move that to the right-hand side and then solve. And to get this to be well conditioned, you typically have to oversample, but it's not too bad. You oversample roughly, well, the number of collocation points is proportional to the number of basis functions. Okay. So before I present the numerical examples, what can you do with this? How can you generalize this to other scenarios other than just the single plate? You can treat separable PDEs and curved boundaries. You can look at arbitrary non-convex domains. That sounds trivial, but it's not to make it numerically well conditioned. You can also look at unbounded domains, which is the content of this talk. And once you have the solution on the interior, you can evaluate quickly in the interior as well. So just some simple observations to keep in mind as to why this could potentially be useful. First of all, it's fast. So even if you're dealing with hundreds of basis functions a second or much less, it's very easy to code and use. You just need to set up this matrix from the Fourier transforms of your functions. It's boundary based, so you get a dimensional reduction. And similar to Wiener-Hopf, you avoid, at least in the spectral plane, having to evaluate singular integrals. And one of the things I'm going to talk about is that you actually have a very flexible choice of basis functions to expand your unknown in. And this can capture things like corner singularities and coupling with elastic deformation, stuff like that. Okay, let's get concrete. Let's look at a simple example that we're all familiar with, that of just an instant plane wave on a single plate. And if we look at this in elliptic coordinates, we can use separation of variables to generate a analytic solution in terms of Mathieu functions. So just a reminder of what the relation I have that I'm hoping to solve. So here I've denoted the jump in Q across the plate, so the pressure field just above minus the pressure field just below by this angular bracket here. And I have these collocation points that I can choose, this collocation set. There is something interesting going on here. This complex set of collocation points is allowed precisely because I've assumed my solution satisfies the Sommerfeld radiation condition. And in fact, if you cross those out and just look at these real values, this is ill-posed, and it's actually numerically ill-conditioned if you try and solve it. And this thing here on the right-hand side, don't worry too much about that. That's just the incident field or the forcing term for this integral equation. Okay, so this is just the same as the Wiener-Hopf equation for this geometry. So we all know this, but you can predict usually from the geometry and the boundary conditions the type of singularities you expect your solution to have. So in this case, we have square root singularities at the tips of the plate. So a natural choice of expansion functions are these Chebyshev polynomials of the second kind multiplied by this square root weight. And the reason I've chosen these is because they have analytic forms for their Fourier transforms in terms of Bessel functions. So you use those for the expansion, and then this is typically the type of result you get. So on the y-axis, I've plotted the relative maximum norm error, well, a discrete version of it, against n, the number of basis functions that I'm using to expand my solution. And you can see for a range of frequencies, so this is k0 is 10, 50, 100, 150, I get rapid convergence down to machine precision, right? So this converges exponentially in this case. And in blue, I've also shown a sort of a state-of-the-art boundary integral method, which was designed for the same problem, which initially converges exponentially, but then tails off because of the difficulty of having to deal numerically with these singular integrals. And here we can see this is just the jump in pressure across the plate, and as we increase the frequency, we end up with a more oscillatory solution. Okay, so you can extend this to more complicated geometries, arrays of wedges at different angles, plates, polygons, curved boundaries, etc. And in general, you get this type of convergence. Okay, so in the last 10 minutes or so, I just want to move on to two applications, which I hope will interest people here. The first of which is elasticity. So we heard yesterday, and when we were hearing talk about owls, that elasticity is potentially an effective way of reducing the noise scattered off objects. The idea being that the elastic plate or object absorbs energy as it oscillates. But currently there's a challenge in trying to develop fast and accurate methods to solve these types of problems. I'll show you on the next slide the boundary conditions you have, which make it difficult. In particular, it's difficult to solve this with Wiener-Hopf techniques. So we have an instant field, hits k collinear plates. In this case, produces a scattered field Q. I'm going to denote on the ith plate, so gamma I, the plate deformation by eta I, and then this plate deformation satisfies this elastic beam equation, where the forcing is given by the jump in the pressure field across the plate. And here are just some physical parameters that I won't really comment on, other than that omega is just the wobbliness of the plate, or the ratio of the bending wave number to the acoustic wave number. And to close our system of equations, we also have a kinematic condition that just says the plate deformation is proportional to the total normal derivative. And then each endpoint of the plate is either going to be clamped or free to move. Clamped if the deformation and its first derivative vanish, or free to move if the second and third derivatives vanish. Okay, so this looks quite horrible to try and solve with a spectral method, right? So for instance, if I try and expand eta in something that captures the corner singularities and then hit it with this fourth order term, I'm going to get something that's non-integrable, and I can't compute its Fourier transform. So there's actually a way around this in this particular case. So if I expand the plate deformation in terms of eigenfunctions of the fourth order derivative operator, I get a really nice representation of the pressure and its normal derivative. So I'm just going to expand here. So these are the eigenfunctions. These are the eigenvalues. This is the expansion. If I substitute this into the relation I had for the normal derivative, I end up with this nice equation here. The jump in pressure looks horribly complicated initially, but then you remember that the fourth order derivative of these functions is just a linear combination of the original function, so you get this nice linear expansion here. So once I've got both of these, I can just shove them into my integral equation, and I collocate again, and I compute the plate deformation, and then I can work backwards to compute the jump in the pressure field. You also need to be able to compute the Fourier transforms, but that's very easy because you just use integration by parts, and you can compute these functions just using standard spectral methods. So the upshot is you get a fast and accurate spectral method for this problem, and you can cope with multiple bodies and plates with different physical parameters such as different elasticity, and you can also add porosity, but I haven't bothered to talk about that. Okay, so an example is the following geometry. So I'm going to consider a single plate of length 1 with a quadrupole incident field just above the end of the plate. So that's supposed to model some sort of sound source. Most of the plate will be rigid, but there'll be a proportion of the plate of length L which is allowed to be elastic. So this is kind of a toy model of, say, a propeller with an elastic tip or a wing or something like that. And what we want to do is see whether the spectral method that I described can give you nice and fast results to be able to see what the far-field sound looks like depending on the parameter L and how elastic the plate is. So some plots. So this is for frequency 5. This is for physical parameters typical of aluminium and air, and different L corresponding to the different proportion of the plate that's allowed to be elastic, and then different elasticity. So in bold I've shown the rigid plate far field, and then as you increase the elasticity you get less and less noise produced. Not surprising. This was for L equals 1. When you halve the length of the elastic plate, similar sort of picture, but when you have a very, very short elastic extension, you get very little noise reduction, and that's purely because the frequency isn't large enough to excite the oscillation in the short portion of the plate. So let's increase the frequency to 50. So this is quite a hard problem to solve numerically, right? Because we've got two parts of the plate, a clamped part and an elastic part, lots of horrible singularities. And you can see the picture is similar for a fully elastic and half elastic plate. But then when we come to only 5% portion of the plate elastic, we see that if the plate is elastic enough, if omega is small enough, we're able to get quite a large amount of noise reduction, about 50%. And you can quantify this. So this just shows the relative power, radiated power at infinity for different omega, for the different length of elasticity. So you get this nice curve showing you get a reduction in noise, and then these spikes correspond to resonances of the plate when the frequency excites the resonance oscillation, and your linear model of plate deformation breaks down. Okay, I don't really have time to go into the physical interpretation of this model and some other results, but hopefully that's shown you that you can use this method in an efficient manner to produce plots like this. So let's just draw some quick physical conclusions from this, which I've already mentioned. Short elastic plate deformations can reduce noise, especially if the frequency is large enough. If you only have a low frequency, then if the plate is too small, you're not going to excite oscillations to reduce noise. So different length extensions should be used for different frequencies, and I'm looking at hopefully extending this to kind of 3D elastic spheres and things like that, but that's another story. So let's move on to the final application, which is that of a perforated screen, which is joint work with Matthew Pridden, who I think is over there. So I'm going to consider lots and lots of plates of length d, and the gap between the plates is going to be just denoted by 2a. And these are going to be hard plates, so I'm going to impose a Neumann boundary condition. Okay, and if I do that, and I'm in this asymptotic regime here, so the gap is much smaller than the plate length, and the plate length is much smaller than the inverse wave number, then I expect that I can model this physical model by just a single plate with a homogenized boundary condition. So this is just a Robin boundary condition, where potentially this coefficient here could vary along the plate. But far from the plate ends, you expect this constant value to be a good approximation. So the problem with this is that, as far as I am aware, so please correct me in the questions if I'm wrong, this hasn't been numerically verified before. And the reason for that potentially is because you have to get a large number of plates, each with singularities at the endpoints, but also the gaps between the plates have to be very small, right? So it's a difficult problem to numerically solve. And then another question is, how do you take mu from this constant value within the plate to be 0 at the endpoints, which is the physically correct thing to do? So I haven't really got any firm conclusions from this, other than that you can use this spectral method for this model. It's very efficient and converges exponentially again. And I'm going to consider for the plots, I'm going to show you just some simple ways of tapering the Robin boundary condition to 0. So here's just the constant value, and then I'm going to consider hyperbolic tan and then an inverse log. So these are going to be noted by mu0, mu1 and mu2. And then here are some typical plots. So I'll go through this a bit slowly just to explain what's going on. So I'm considering different values of that ratio, right? So to be in the asymptotic regime, these numbers have to be large. So this is really when you're starting to hit that regime where we expect the model to work. In red, I've shown what happens when you just treat this as a single plate with a rigid boundary condition, and you get a lot of scattered noise. So this would actually kind of go out of the picture and hit the ceiling and then come back. In black, I've shown the true value, which is the thing computed by the far field noise computed by the spectral method, where you have lots of small close plates. And then I've shown what happens when you have different values of mu. So blue is constant, purple is that inverse log. No, purple is hyperbolic tan, green is inverse log. So you can see that as you go to the asymptotic regime, they all seem to agree, and it doesn't really matter which one you take. But when you're quite far into the regime, it seems to make quite a big difference how you taper it to 0. And I haven't really got beyond that in this physical model, because I'm not really an acoustic or fluids person, but I'd be interested to see if anyone has any comments on that. So I can just say at this point that you can produce these plots very quickly and efficiently using the numerical method. Okay, so some conclusions to wrap up. I've developed a fast and accurate method for scattering problems that are difficult to analyze analytically using the Wiener-Hopf method. You can view this as a Fourier transform of the boundary integral equations with collocation occurring in Fourier space. Well, I should be careful here. It can be easier to use the more accurate than boundary integral methods because there are no singular integrals. There are ways of dealing with the singular integrals efficiently with sparse systems, but I won't go into that. And suitable basis functions can capture the relevant difficult boundary conditions in when you couple to plate deformation and things like corner singularities and that sort of stuff. So just some open problems to finish on. Can this be efficiently implemented in 3D? You can set up the integral relation in exactly the same manner, but now you have to analyze the singularities, right? So you no longer just have corner singularities, you have edge singularities, and that can be quite difficult because you need to develop bases for that and be able to compute their Fourier transform even when the frequency is quite large. Nonlinear boundary conditions are something I'm looking at with Newton iteration. Can you somehow leverage the connection between the unified transform and the Wiener-Hopf method? We saw this was kind of equivalent in the collinear case, but can you go outside that and somehow can that give you information about how to extend the Wiener-Hopf and potentially tackle problems? And finally, is there a unified way of viewing everything? Okay, thanks for listening.
Any questions?
Returning back to basics, right? When you and the promotional part for the unified transform method, right? You had a long list of extensions and advantages, right? At some point, among them.
This.
Yeah, I think this item right on the top: separable PDEs and curved boundaries.
Yes.
Am I right in thinking that, yeah, you might have a separable PDE whose a kind of
I can.
coordinate surfaces are curved, right?
Yeah.
And the boundary may be curved, but it must be one of those coordinate surfaces, right?
So you can set up setting up the integral relations, not a problem. You just
So coordinate lines, rather, right?
yeah. Instead of taking these harmonic waves as V, you just take a separable family of solutions, which you have because it's separable. So you just need a numerically efficient way of doing that, and you can do it with there's a trick with Chebyshev polynomials that allows you to make it efficient.
Okay. On the error plots you showed, there was a flat bit, then an elbow, then they went down.
Yeah,
That's well
yeah.
understood regarding
I get asked
enough
about that a
basic
lot.
functions to
Yeah.
resolve the smallest length scale.
Exactly.
But I just wondered if you have an analytical formula for that, because you mentioned those Bessel functions, which just happen to come out exactly in this.
Mm.
Where argument equals order, that's where something definitely starts to decay. So you might actually, I don't know, have an analytical formula for your error plots.
Possibly. I haven't really looked at it analytically. I know that this typically the bit where you start to see this convergence scales linearly with the wave number, which is kind of what you'd expect. But yes, it's possible you could develop. I mean, and actually, when you compare this, so the way you compute the solution with Mathieu functions, you end up expanding each Mathieu function in a sign basis in elliptic coordinates, which when you map back to real space is equivalent to those Chebyshev polynomials multiplied by the weight. So you're actually in effect using the same expansion basis as you would if you were applying separation of variables. So potentially there's a way of leveraging that to see to get a formula. But
I'm curious, what happens with this nice technique if you have embedded inside one of your cracks would unfortunately move because you have vibration and you have fatigue in material, and the crack would like to propagate as a result during all this process. So what happens with the technique?
oh, like a time-dependent version.
Yes.
I don't really know. I am starting to look at some time-dependent problems with this method, but yeah, it would be certainly difficult to set up a spectral method in time as well, but it could be possible.
Just half comment, half question to the speaker, maybe to the audience, because it's kind of, you made special emphasis on comparisons and highlighting advantages compared to Wiener-Hopf approach. I think you mentioned in brackets amongst others, right? Like competent methods, Wiener-Hopf as possible in the list of predecessors, right? Earlier methods versus.
So you're asking whether I've compared it to other.
Trying to expand the list, right? I think you did say.
Yeah.
Wiener-Hopf, for example, right? Among others.
Yeah.
Comes to mind not only to me, I mentioned to some people in the audience a related predecessor, the Sommerfeld-Maluzhinets method, right? And in fact, Larissa Fratkin mentioned the words approaches due to Gilles and company, for example. Not only basically idea to have scatterers with locally flat surfaces do spatial Fourier transform and reduce the problem ultimately to integral equation in the spectral domain with all the advantages you have.
Okay, that's interesting. I wouldn't be too surprised then if what you get is actually the same integral relation just with a different parameterization.
Provocative part of a question. Any particular problem for which all the previous methods fail, but the uniform transform method?
So there's an example for solving things analytically on a triangle, which you can do with the unified transform, but you couldn't do with previous methods. It's one example.
Okay, let's thank the speaker again.